We are going to discuss indirect band gap semiconductors. If minima of conduction band and maxima of valence band occur at different values of momentum, then such semiconductors are called indirect band gap semiconductors. Consider this figure. Already I have said that decay diagram looks like parabola. X-axis is momentum represented by K, and the y-axis is kinetic energy represented by E. The energy difference between conduction band and valence band is denoted by energy band gap Eg. So look onto this diagram. Here the minima of the conduction band, that is I am indicating with a blue color, and maxima of the valence band are occur at different values of momentum. Here the minima of the conduction band having the momentum value k dash, the maxima of the valence band having the momentum value k equal to 0. So this type of semiconductors are called indirect band gap semiconductors. For example, silicon, germanium are indirect band gap semiconductors. So silicon and germanium cannot be used for the fabrication of light emitting diodes. I have already stated that direct band gap semiconductors are used for the fabrication of so silicon and germanium cannot be used for the fabrication of light emitting diodes. Okay, so the example for direct band gap semiconductors are gallium arsenide, gallium phosphide, gallium nitride, and etc. So remember, silicon and germanium are the indirect band gap semiconductors. These are not used for the fabrication of LED. Then again consider the previous diagram. Here I have already stated that the minima of the conduction band and the maxima of the valence band occur at different values of momentum. Again I am drawing this diagram one more time for explaining one more concept. Here one electron is occupied at minima of the conduction band. This is one free electron. Then at the valence band, one hole is there, and this is energy band gap indicated by Eg. Then at the time of recombination, the recombination in indirect semiconductors done by the two-step process. That means here one free electron is excited at the conduction band. Then I have already told that the excited states are highly unstable state, so the free electrons want to come into the valence band. So while coming to the valence band, that means recombination. The indirect semiconductors recombination is taking place by the two-step process. Consider one intermediate level ER, one intermediate energy level ER. In indirect semiconductors, the recombination is two-step process. The first one is the free electron is moves into intermediate level ER by changing momentum and energy. So first free electron is occupied into intermediate energy level. Then this electron moves from intermediate level ER into a vacancy occupied in the valence band by changing or releasing energy. Such a two-step recombination is called indirect recombination. Okay, so here for indirect band gap semiconductor, indirect recombination is done, which is done by two-step process. First is free electrons move into intermediate level by changing momentum and energy. After that, electrons moves from intermediate level ER into a vacancy in the valence band by changing or releasing the energy. Then when they are coming to the hole present in the valence band, they are releasing energy. But this energy is not in the form of light. This energy is in the form of heat. During the indirect recombination, energy is released in the form of heat or phonons. So I am writing the point here. During the indirect recombination, energy is released in the form of heat or phonons. Whereas in direct band gap semiconductor, the energy is released in the form of light. That is why direct band gap semiconductors are used for the fabrication of light emitting diodes, and indirect band gap semiconductors are not used for the fabrication of LEDs. Next again, we are coming into the topic, the light emitting diodes. It is a heavily doped PN junction, PN plus, fabricated from direct band gap semiconductors. Already I have explained the LED is operated in forward bias mode. Then the next point is the LED can emit visible light as well as infrared light. A visible light LED are fabricated from direct band gap semiconductors whose energy band gap lies between 1.75 electron volt to 3.2 electron volt. Electron volt is unit of energy. LED can emit visible light, also infrared light, depending on the energy band gap of the semiconductor. Human eye can detect light if the photon wavelength lies approximately 0.4 micrometer to 0.7 micrometer. A human eye can detect light if photon wavelength lies approximately 0.4 micrometer to 0.7 micrometer. Such a radiation of photons is called visible light. Infrared light is called invisible light because human eye cannot detect infrared rays. So LED can emit visible light as well as infrared light depending on the semiconductor we are choosing. The one type of direct band gap semiconductor is gallium phosphide, GaP. Ga stands for gallium and P for phosphorus. GaP has energy band gap of 2.26 electron volt, which corresponds to wavelength of 0.54 micrometer. Therefore, it is used in the fabrication of green color LED. Already I have derived one expression for wavelength lambda in micrometer is equal to 1.24 divided by energy band gap Eg in electron volt. Okay, when you substitute the value of electron volt of 2.26 in this equation, you will get wavelength of 0.54 micrometer. So this one is important question. The gallium phosphide emits green color LED because their band gap is of 2.26 electron volt. Depending on the band gap energy, they are emitting different light. Next is gallium arsenic phosphate, GaAsP, is a direct band gap material whose energy gap can be varied by changing the composition of phosphorus and arsenic. In the case of gallium arsenide phosphide, I can change the energy band gap. So as to I can change the color of emitted light by changing the composition of phosphorus and arsenic. It is useful for the fabrication of LED, which can emit yellow, orange and red light. Depending on varying the composition of phosphorus and arsenic, these LED can emit yellow, orange or red light. So the gallium arsenic phosphate can emit three types of color: yellow, orange and red. So here I am writing gallium arsenic phosphate AS. In the bottom of arsenic I am written 1 minus X. Then the bottom of phosphorus I have written X. X is the mole fraction of phosphorus and it can be vary from 0 to 0.45 according to energy gap will vary. We can vary the mole fraction of phosphorus from 0 to 0.45. Why it is I am choosing a limit of 0.45? Because if X is greater than 0.45, it will become indirect band gap semiconductor. So that I can't use for the fabrication of LED. So the maximum value of X is limited to 0.45. The next type of direct band gap semiconductor is gallium nitride, indicated by GaN, has energy gap of 2.6 electron volt, which corresponds to a wavelength of 0.47 micrometer. Therefore, it is used for the fabrication of blue color LED. So the gallium nitride is used for the fabrication of blue color LED. The next point is infrared LEDs are fabricated from direct band gap semiconductors whose energy gap lies between 1.24 electron volt to 1.65 electron volt. Invisible LEDs, that means infrared LEDs, are fabricated from direct band gap semiconductors whose energy between 1.26 electron volt to 1.65 electron volt. For example, gallium arsenide has energy band gap of 1.42 electron volt used in the fabrication of IR LEDs. IR means infrared. So remember, depending on the value of energy band gap, the LED is emitting infrared light or visible light, and also the variation in the color of visible light is also depending on the band gap energy. When the LED is operated in forward bias, holes are injected into the N region and free electrons are injected into the P region. These injected carriers keep recombining with majority carriers. Due to this recombination, energy is released in the form of photons or light. For example, this one is energy level of a conduction band and the bottom energy level of valence band. when the electron is fall from conduction band to valence band and recombining with holes present in the valence band. I will write with a different color. This one is hole. This one is free electron. The free electron present in the conduction band is fall into the valence band and it is recombining with holes present in the valence band and energy is released. Okay, when the recombination happens, the energy is released. That is in the form of photons or heat. But in the case of direct band gap semiconductor, the released energy is in the form of photons. So energy is released in the form of photons or a light, where that released energy E is equal to H into F. This emission of photons when electron fall from conduction band to valence band is known as spontaneous emission. So the LED has spontaneous emission, whereas laser it is stimulated emission. LED has a relatively greater voltage drop 1.2 volt to 2.6 volt and they operate at higher currents, that is tens of milliampere. So I am writing one more circuit diagram. One resistor that is connected to a LED. LED symbol is like that. Normal PN junction diode. Then we have to draw an arrow mark. That means they are emitting the light. This arrow mark indicating that this LED is emitting light. Then I am connecting a voltage source, a battery, a cell. For example, it is a cell of magnitude V. Then the resistor R is used for the limiting the current for the smooth working of LED, or I can say the resistor is limiting the current so it helps to preventing the damage of LED. If I am not using the resistor, sometimes a heavy current, a large value of current is flowing through this flowing through this circuit that may result the damage of LED. In order to avoid that I am using the resistor R, which is called current limiting resistor. Okay, here look onto this diagram. Here the positive terminal of battery, that means this one, is connected to P side of the LED. The negative terminal of the battery is connected to N side of the diode. So I can say this LED is operated under forward bias mode. As a result, a current is flowing indicated by I. I can say I is the forward current. Then this voltage drop when the diode is in forward bias, a voltage is developed across the diode. This is indicated by Vd. For an ideal diode, this voltage drop is 0, but practically LED has a greater voltage drop 1.2 volt to 2.6 volt. Why it is I am saying that it is a greater voltage drop? Because for a normal PN junction diode, the forward voltage drop, let it be Vd, is of 0.62 to 0.7. That will vary depending on silicon diode or germanium diode. So normal PN junction diode, it is 0.6 to 0.7 volt. But for an LED has different construction. So LED has a relatively greater voltage drop, 1.2 volt to 2.6 volt. And also the LED operate at higher currents. That means through the LED, a large value of current is flowing. That is tens of milliampere. Okay, LED can hold at a higher amount of currents. For an LED, intensity of emitted light is proportional to forward current. That means, again look onto this diagram. If I am varying the supply voltage, or if I am increasing the supply voltage, as a result, the more current is flowing through the circuit. As a result, the LED, in the case of LED, the intensity of the light is increases. That is, for an LED, intensity of emitted light is proportional to the forward current. Next one is one parameter, optical conversion efficiency. Efficiency means output divided by input. Here, the optical conversion efficiency of LED is the ratio of optical output power and electrical input power, because in the case of LED, the output is light. So, the output power is an optical parameter. Then in the case of LED, the input is supply voltage, electrical parameter. So the input power is electrical power. Both are expressed in watts. The next point is LED have spontaneous emission in which released energy is greater than or equal to energy band gap Eg. As a result, photons released may not have same wavelength or same frequency. Hence, light emitted by LED is not monochromatic. To obtain monochromatic light, laser diodes can be used. Monochromatic means the emitted light is not in the same wavelength. Okay, so here I am saying the direct band gap semiconductors are used for the fabrication of LED. Then they are emitting the light. These emitted light are not in the same wavelength. That is why they are known as the LEDs are emitting not monochromatic light. Okay, the example for monochromatic light generation is laser diode. Laser diode is emitting the monochromatic light. That means the emitted light have the same wavelength, whereas in LED it is not monochromatic light. The next point is application of LEDs. What are the applications of LED? The first one is lighting or the traffic light systems, because LED producing several type of colors, visible light. So we can green, orange, yellow, blue color. So these LED can be used for the lighting, decoration purpose, and also traffic light systems. The next one is remote controls. In remote controls, for example, TV remote controls, they are using invisible light LED, that means IR LED. Okay, so the remote controls and also the LEDs are using. Then indicators, then for opto isolators, and optocouplers. Then the next is it is used in optical fiber communication. It is used in optical fiber communication. As optical source. We all know that in optical fiber communication, the information is transmitted in the form of light. Here LED is emitting light, so LED can be used as a optical source in optical fiber communication. next we can do one small problem depending on related to the wavelength. So here I am writing the question. The question is, an LED is fabricated using a direct band gap semiconductor what is the emission wavelength of the radiation. What is the emission wavelength of the radiation? Given that energy band gap is 2.5 electron volt. Okay, so the question, we have to find out the emission wavelength of the radiation, or I can say what is the wavelength of emitted light, indicated by lambda, which is equal to 1.24 divided by band gap energy in electron volt. Then and this unit, the wavelength unit is micrometer. So remember that the band gap energy is expressed in the form of, or the unit is electron volt, and the lambda unit is micrometer. Given band gap energy Eg is equal to 2.5 electron volt. So substitute value of Eg into lambda equation. So lambda is equal to, wavelength is equal to 1.24 divided by 2.5, which is equal to 0.496 micrometer. So the wavelength of emitted radiation is 0.496 micrometer. Next we are going to see what are the applications of LED. So I am writing the heading. Next we are going to see what are the advantages of LED. Already we have seen that applications of LED. Next we are going to see advantages of using LEDs. LEDs produces more light per watts than incandescent bulb. This is useful in battery powered or energy saving devices. So the first advantage is LED produce more light per watt than incandescent lamp. What is the unit of power? LEDs produces more light per watt than incandescent bulb, so it is useful in battery powered or energy saving devices. The next point is LED can emit light of an intent color without the use of color filters that traditional or lighting method require. So, in order to produce the different color, an LED does not require any color filters. So, here I am writing point only, does not require any color filters to produce the different colors of light. The third point is LED can have a relatively long useful life. An LED has a lifetime of about 50,000 hours. LED has a lifetime of about 50,000 hours, whereas fluorescent tubes typically they are rated at about 3,000 hours. So the LED provides more lifetime. The next advantage is LEDs light up very quickly. A typical red indicator LED will achieve full. So the LED light up very quickly. That means when you switch on the power supply, the LEDs immediately turn on. LED lights up very quickly. The next advantage is when used in the application where dimming is required, LED do not change their color tint as the current passing through them is lowered, unlike incandescent lamps which turns yellow. Okay, when we want to need an application where the dimming is required, the LED do not change their color. Okay, that is in dimming applications. That means we have to slightly reduce the intensity of the light. Okay, in dimming applications, LED do not change their color tint. Okay, these are the advantages of LED. The next one is disadvantages. LEDs are currently more expensive as compared to incandescent lamp, fluorescent lamp are currently more expensive, but nowadays these are cheaper. The next disadvantage is LED performance largely depends on ambient temperature of the operating environment. LED performance depends on ambient temperature of the operating environment. This will not significant in our climate temperature, but their performance is depends on the ambient temperature of the operating environment. Okay, these are the some disadvantages of LEDs.